Okay, welcome back to the discussion session with our two speakers from this morning. We have 1 hour, and I already saw a hand by you, Marie, so please go ahead.
You said that the program could be discussed could be wrong or whatever. So what do you have more in mind? And kind of consistency checks of the approach, or the falsified from
No, so I'm worried about the consistency. See, we have in the construction, I defined an emergent space at a particular time. And then I interpreted, so in terms of submatrices. And then I interpreted the extent of space parameter as physical length. So this is a proposal. And this proposal might not be correct. So this is one thing that I'm worried about. So if the extent of, so if the way that we are interpreting the emergent space at a particular time, if this is correct, then I'm comfortable with having a metric emerge. So that's number one that I'm worried about. Number two, I was talking about the space being spatially flat. That's the thing that emerges. So the fact that it emerges as infinite, that's natural. That one can show using the Riemann-Lebesgue lemma. Now the fact that it's, see, for finite n, for finite size of a matrix, it's finite. And the size is proportional to square root of n times some fundamental constant. But then in order to get the fact that the metric is really homogeneous within that patch, I use the fact that the off-diagonal matrix elements, their expectation values are approximately constant if you're not too far from the diagonal. For that we are taking from the numerical simulations, and we do not have analytical control of that. So that's number two that I'm worried about.
Let me remind you of the convention. Full hand is new question, one finger is follow up. I think we had Bo, then Kelly, then you. Oh, you follow up.
So it's a follow up.
Okay, then you follow up and then you.
So you said that also time emerges because you start from a state of high temperature. If I remember correctly. Right?
So I'm starting with a matrix model, which has a time, but then I'm putting that matrix model in a finite temperature state. So there's no evolution then. And so then what I have to do is I have to use the temporal matrix to get the emergent time. Now that part of it is standard.
Physics.
Sorry?
Temperature, whatever it is, you have equilibrium.
That's why there's no evolution in terms of the time of the matrix model.
This implies a notion of time, because how can you define equilibrium if you have no notion?
That's right. So there is a time in the matrix model, and the physical time is absolutely unrelated to that. It is not even a clock in our emergent space time. The remnant of the BFSS time is the temperature, and the temperature is reflected in the amplitude of the cosmological perturbations.
It's like a cosmological time?
It's not a cosmological time.
Okay.
Yeah. You have a follow-up, sorry. Right. It would be helpful to get clear this for me. The matrix model you're talking about, it's you're also saying VFSS, which is
Right, and I gave a Lagrangian.
but VFSS. How should I say this? It's there's a superstructure there, which is it's usually done in the infinite momentum frame, and here this is more. I think
See?
you're talking about the matrix model.
That's right. I'm talking about the matrix model.
Matrix.
Yep.
Which is essentially an infinite number or large n number of B branes.
That's how it was derived. That's how it was motivated. Let's forget about where the motivation comes from. Let's take it as our starting point.
That's then
This is our starting point.
This model is then.
And you see what I was trying to do in this new part, which I never presented before. I was then trying to see how do the strings actually arise in that matrix model.
In also on the precise formulation of that model, you did take the standard truth limit, right?
Yes.
Which is not always done in the BFSS.
That's right.
context.
Absolutely.
And for me, this makes it much more interesting. So, good.
So maybe you can find out where it fails.
Fails.
See, I'm worried. I'm worried that there might be something wrong because I'm not a string theorist.
Follow-up comment and a question. Follow-up comment is that I asked you about the P and the P. I think that after looking what you do, it seems to me that P is an order parameter. In fact, it goes in the temperature. It doesn't go in time. The time is a knot.
Mm-hmm.
So
yeah.
To me, it would be, I prefer to think of it in this way, not as a time at all, but the pre-existing, time, absolute time in which you're doing your exercise. That is an order parameter of your math.
Okay.
And it's natural then to see that goes into the temperature from that point of view. And the other comment I had is that the fact that you find this flat space, and the way you do this, and this is just a question of my ignorance about the model, is that can you interpret the n going to infinity limit as an hydrodynamic limit? Are you sure that you are not taking something like an infinite volume with respect to the typical interaction scale of your term model? Because that would make much sense then that the emergent geometry is especially flat. Because the geometries are always especially flat, for example, if you...
Okay. Yeah, thanks a lot for that comment, because I think I agree with what you said.
But if someone has described that transition in these terms as an hydrodynamic limit?
I don't think so.
You said you were breaking supersymmetry. This is when you were putting in D1 branes.
No, the background. The background is a background in which the bosonic matrices are excited. And then in computing, so also the strings that I put in, they are excited. They are configurations of bosonic matrices. But then in computing the effective action, you basically introduce both the fermionic fluctuations and the bosonic fluctuations.
But you said you were mentioning that you still had a zero force condition. That's a hallmark of some unbroken supersymmetry. That's an
Fine. Fine.
You may break some of your initial supersymmetry, not all.
Yes.
And also that's related to the fact that you're not getting a cosmological constant, which is another indication of unbroken supersymmetry. Yeah. So are you going to break that supersymmetry at some point in the future? One generally does.
Yes.
I work in a world where supersymmetry is around because I like it. Eventually, I have to have lunch.
We studied this in detail in string gas cosmology, and it will work exactly the way it worked in string gas cosmology. So the fact that okay. Yes, so this now gets into the things that we still need to do. There will be a dilaton, and in this model, and the dilaton will need to be fixed. And in string gas cosmology, we did that by adding a mechanism called gaugino condensation that naturally broke supersymmetry. So this is what I have in mind.
That's a deep, yeah.
Yeah, I take your
Saying much more about this theories.
right.
And wants to say something.
Yeah, follow up first by board and then your question.
Yeah, it's all connected. Supersymmetry and breaking the time, and it's intriguing. You're saying that you have an emerge, the time emerges, and you're starting from a temperature. I assume that you mean by taking the real, taking temperature as being imaginary time circle, and then you think about time as emerging through some continuation.
Now you see time, the emergent time that comes from the A0 matrix.
So, but you do have temperature, because otherwise you can't have non-zero A0.
Yeah.
And temperature, doesn't that help breaking supersymmetry as well? Or is it irrelevant?
It can be, if you go back to Paris, Parisi-Sourlas. I was wondering if your time is really a secret Parisi-Sourlas extrapolation. Your T.
Yep.
Is that what it is? Because that's really.
I have to go back to the literature. It sounds reasonable. Yeah, I know the work that you're referring to, but I haven't read it since I was a PhD student. That's it. Yeah, thanks.
I was struck, you said that you had a dilaton. Presumably you also have the pseudopartner, the axion. So you potentially have dark matter and dark energy. I don't know why you have to fix the dilaton.
Fix.
Because in string theory, the dilaton has a runaway potential. And it could, if it runs down to its minimum, it could act as dark energy. I've never managed to get it to work properly, by the way.
We tried as well. We also failed because we failed to get, with that running dilaton, we failed to get an equation of state parameter, which is sufficiently negative. So I don't think this will work.
Just say, and I couldn't get the screening, the forces. The dilaton, of course, couples to everything and will give a fifth force.
I think dark energy is more subtle.
Anyway, but you do have the dilaton and the axion in your model.
Well, not yet, but we need to extract it. So that's all part of the program. See, the dilaton is a field corresponding to a particle excitation. So I first need to really find the particles, and then I want to see that you get Newtonian gravity, that you get the correct Newtonian limit. I think this is where I'm going first, because if that fails, then the program fails. So there are many ways where it could fail in the future. So.
Well, my question will be about the matter content. We have a discussion here that scalar quintessence is not good. So what quintessence, by your opinion, is better? Can we consider vector quintessence, perhaps even lens breaking quintessence? I saw some attempts to
No, so now this is my bias, my personal bias, And my personal bias is that dark energy is such an interesting discovery, such a fundamental discovery. It is telling us something very subtle. No quintessence. It's not quintessence. No kind of quintessence. But that's my personal bias.
Cosmological constant.
The cosmological constant vanishes. There's no cosmological constant. That is clear.
Well, from
yeah,
because from my perspective, coming from loop quantum gravity, besides the fact that so far as I know in string theory you also have possibly a negative cosmological constant. This is different, but so the perspective I come from is the one in which having the cosmological constant as part of the theory makes everything nicer. And so you need it somehow, it's not needed, but it's an ingredient that makes everything finite. That comes quite naturally in the theory as simply the curvature of your units of space-time.
Yeah, so here in this setup, there is no cosmological constant. And there's an infinite space. And if that creates problems will have to be dealt with.
Well, yeah, I'm not sure I would be. I mean, there isn't a cosmological constant in the sense that you don't generate that, but you were assuming Einstein field equation. Mm-hmm. And if from your model you derive the Einstein field equation, how do you know that you don't get geometrical?
No, I was not using the Einstein field equations in no way. When I wrote down that power law for the effective scale factor, this was solving the matrix equations of motion. This was not solving the Einstein equations of motion. This was in the large distance limit, the quantum. That's for the fluctuations. Okay. That's for the fluctuation. For the fluctuations, I'm using the Einstein equations because I'm only dealing with length scales, which are centimeter and more.
Yeah, but what I'm saying is that, so I don't disagree with your result that you don't have a cosmological constant. What I say is that imagine now you will, in the future, check if your model can reproduce in some suitable limit the Einstein equation so that your treatment of the perturbation can be, self-proved. You may still find by completely different origin a cosmological constant popping out.
That's possible.
Yeah, so as far as I understood, there are two emergences in the proposal. One is, let's say, less fundamental as regards the scale factor, going from a finite constant value to a value that is available. And the more fundamental one that regards the fundamental layer that was mentioned a lot yesterday. And some way in between these two emergences, there is from the starting point to the second emergence, so the one related to the transition of the scale factor, there is this matrix theory and the string gas cosmology proposal, right? So my question is, there is a way that is there a way that is still appealing to you that say the second emergence, so the one related to the scale factor, going from a finite constant value to an evolving scale factor, but which does not involve string as cosmology and string theory, so of a different origin, but still with the emergence universe related to the scale factor transition?
Well, I think the answer is yes, and I think Stefano will be talking about that. He will be talking about another approach. So basically, there's nothing exclusive in what I was talking about. I was saying, let's take one particular well-defined starting point, which is motivated by string theory, this BFSS model, and let's see what we get.
So there are other possibilities for the emergent universe which do not rely on string as cosmology.
Yeah.
I have actually a question on the emergent scenario. And it's also a question, it's a general curiosity of mine, and it's also, I have a similar curiosity also for the matter bounds. And because when you were showing something that was like this for the emergent universe. And my question, so there was something similar that Stefano studied some years ago related to with Alessi, yeah. Yeah, that's exactly my question. So, so yeah, so I was wondering, is this compatible with the presence of some oscillations before the actual expansion? And if yes, where would they come from, and what effect would they give in this case?
Okay, so at the level that we've analyzed this, we don't see the oscillations, but there's no incompatibility. It's also compatible with having a bounce, with a long emergent phase.
Yeah.
So, but maybe let me make a suggestion here. I think I shouldn't monopolize the discussion, so I think we should also direct questions to Francesca.
Yes, the two hands, Anne, and then.
I was very curious about your hyperborean black holes. I think you had the Planck scale black holes of 14.3
Yes.
micrograms.
Yeah.
So I have to admit, I haven't done the calculation, but they presumably evaporate by radiation.
No, this is what is left after the evaporation. So this is the object. So the idea, that's exactly the point. So in the oldest idea regarding Hawking evaporation, one hypothesis that was not backed, I think, by any calculation, was that the evaporation gets all the way through. And actually, in that case, you would have the emission of super high energetic particles. In fact, even you have a problem of transplanckian modes, because if you go beyond what I am presenting here, you have your black hole that shrinks below the Planck length. So you have conceptual problems, and also we don't observe in the universe burst of cosmic rays such a high energy. So it was actually a problem in the pathology of the old models. So here the idea is that when you reach the Planck scale, you have the transition of so you can be conservative and go all the way through your evaporation, but then when you reach the Planck scale that corresponds to the Planck area, then you stop the evaporation. You have the transition to a white hole, or actually, as I was saying, to this hybrid superposition of black and white states, and then you have this very, very stable particle that can last basically forever. And one problem in the old models was also the fact that they wouldn't accommodate for microstates, because if you go all the way through with evaporation, of course you eliminate everything, including all the interiors. So here instead you have the fact that the throat shrinks, but you preserve the interior. The interior takes much more time to be reabsorbed. So you have microstates inside that can accommodate for the information that is entangled with the information that is in the exterior because of the evaporation.
It's absolutely stable and not stable.
They are not absolutely stable, because in a time that goes as m0 to the fourth, they disappear. But the problem, so if you take a stellar, even if you take Well, for very, very small black hole, they can disappear even within our universe. But if they are black holes, if they are remnant that are the result of the evaporation of a slightly microscopic black holes, then yeah, then they will stay there for a very long time.
Before chat that don't overclose the universe.
But I don't think well, the thing is, I don't think there is this problem in the sense that whatever you do with your cosmological model, you always, of course, so on one hand, you have the theory about what are these objects. And then the viability of this proposal relies on suitable cosmological models in which you have their presence being compatible with all the constraints that we have from cosmology. So of course, whatever cosmological models you want to make, whether it's an inflationary model or whether it's a matter bounce and so on, you want them not to be more than the observed dark matter. And when I say observed dark matter, I mean also the amount of dark matter that we will have in the primordial universe. So we know that dark matter is present in the primordial universe because it's needed for structure formations and so on, even in the early universe. So we know that there is already dark matter there. But we don't want to, so we have to fit our model, our cosmological model, to the constraints given by cosmology. So fitting the production mechanism with the amount of dark matter that you have in your model. And of course, so you depending on the formation mechanism, again, this could be easier or more difficult. If you wanted to form them with an inflationary model, you have strong constraints. If you get them from a previous universe, then you can be free completely to fit your parameters without much constraints.
So if I understand your picture is that you form a black hole, that this evaporates by Hawking radiation, and then when it is basically of the order of the Planck mass, it starts to be in this superposition state.
Yes.
And then it is long-living with a time scale to the 4.
Yes.
So you have m cubed, which is the typical time for the evaporation, plus m to the 4th, basically.
Yes.
The only problem I see, I mean, you presented two models of basically this black hole. Once, I mean, these are black holes which are regular in a certain sense, because you have in mind that at the end they bounce in a certain sense. But in order to have a regular black hole, you have all the model with the inner horizon, or the model that you show, the other class of model, the one with the inner wormhole, space-like wormhole throat. That then, the one with the inner horizon, let's forget about the mass inflation instability. But even if you take just into account Hawking radiation, the Uru state is known to be singular on the inner horizon. Is something that was, something that to my complete surprise was discovered very relatively late. It was basically initially understood by Walden collaborators. They were trying to see the consistency of inner horizon after the paper by Cardoso, or the cosmological constant could allow to stabilize apparently also that paper, I mean, mass inflation. But later on, there is a recent paper by Baldi and Fabri, where they showed that inner horizon basically is an instability in the Uru state, which is ruled by the difference of the square of the surface gravity between the outer and inner horizon. This instability is very fast. So it seems to me that the M cube is not there.
No, but wait. M cube or M4?
M cube is the, no. The M4 is the, if I understand correctly, this is why it was.
But so you're saying
time to wheel the scar in space-time once you reach the remnant state, right? But the M cube is the time you need to evaporate in the first place. It will become Planck scale.
So imagine. So what you're saying is that beside what will be the outer horizon, you may have something like this.
what's in your diagram, but
Yeah.
you had that kind of black hole.
Yeah.
One was even written.
Yeah. And if you are, if I am understanding what you are saying, is that through the evolution you have this part of the horizon that is unstable, so it's moving, and it's like going like this, and this.
Not the evaporation time is just talking radiation, which is an adiabatic process.
Okay.
The stability at the inner.
And what how faster, m square or even less?
There is a recent paper by a guy called Macken from Care that is saying that we form, even in Care is present, it's not a regular, but anytime you have an inner, say that you would form a space-like singularity in an amount of time which is like crossing time.
Also m, but m is too short. Even though.
This case is saying that you get basically something that is a radiation from Care, so you still would have probably an outer horizon.
So, okay, so if this is the scenario, you would make me very happy. Because, so at the very beginning, 10 years ago, I was studying a model in which the instability given the black to white transition was at the time m square. And then I had a bit to put this aside because all the calculations that we were doing. Exactly. And so M was too short, and we focused on a more conservative scenario that is the end of evaporation. If instead you have an instability that appears earlier, my understanding would be that you still have a black to white transition. So what will happen, what was my understanding was that then you have basically the inner horizon that goes back matching the outer horizon, basically annihilating it, making it disappear.
The stuff that at the moment is not the natural outcome you would expect is that this phenomenon is there as long as there is an algorithm that the surface gravity are different. Another possibility is that you can make the black hole extremal without squeezing it to zero.
I see.
And there is a class of extremal.
Extremal meaning very high spin.
No.
No.
There are geometry we wrote recently, let's say, where we found out that there is a class of geometry which are Kerr-like. We know maximal spin, but all the horizon are degenerate and extremal, and they are not suffering this instability. This could be another. We don't know the end point. What I'm telling you, I don't know the answer. The people claiming that there is a space-like singularity, like in Schwarzschild, which I don't believe because it doesn't take into account quantum gravity, which was the motivation.
Yep.
Or that you may have a totally extremal black hole, even if not maximally spinning, which that could be a candidate for astrophysical black hole. We simply don't know. I'm just saying that is a cautionary measure that it's not obvious that there is the m cube before the m4. Because there is a process, there is a very clear instability, both classical by mass inflation and semi-classical by this incompatibility of the Urro state with the inner horizon, which is not so surprising because you know that the Urro state is incompatible with the white hole horizon. The inner horizon is the white hole horizon inside out. So all in all, the timescales could be very relevant for phenomenology. Was a comment in that direction, and it would be very interesting to understand this other part.
Yeah, I am super interested. I had my student Farshil Soltani that was studying all your papers started a year ago. So, but then he graduated and became a postdoc. So I haven't, but he's still working on this stuff. So maybe we can hear from him. So of course, for me, from the phenomenological point of view, this is super interesting. Whatever brings the lifetime to be shorter can lead to more cosmic rays potentially be released. So this could be super interesting. We can use some of the results that were developed back then for them square explosion. There is still something that, so my understanding in a certain sense has evolved, but also has been more and more puzzled. And here maybe you have some ideas. So something that we have been understanding better and better is the fact that so when you look at the singularities for the black hole, you have, of course, here you have a singularity that, I mean, in the classical case, here, the singularity is space-like. So you have a separation between what happens inside the star. So this is the region in which you have the star that is collapsing and eventually bouncing, and we understand well what's happening there. Then here you have a vacuum region that also we understand that is possibly transitioning from a contracting to an expanding geometry. And then we have a third separated region that is what happens really at the horizon. And so these are like three separated phenomena that needs to be described separately. So here we understand, here we have to use full non-perturbative quantum gravity because it's really where you have a full tunneling process, so a quintessential non-perturbative effect. And so, but then now I am puzzled because, so if you continue this diagram and you have the star that is here, I'm not sure what will be coming out here. If the star comes out, maybe comes out later here. I don't know. I don't know if you have a better, even a heuristic understanding of what's going on, because here I am already in a white hole phase, but the star is very far away.
Yeah, but only light that can escape from that.
Yeah.
But that is telling you one very interesting fact that is often unappreciated. That given that the structure across, if you take an horizon, the rays are peeling away this way, the light rays. In a white hole horizon, they're accumulating this way.
Yeah.
So if you want to join them, you need to have a region which is non-classical outside of the joint point. It means that there is a non-classical new physics region outside of the horizon. And that is a very, very big opportunity to see something. At that moment, you have really that there is no shielding in that very narrow region because you have to glue these rays going this way with the greater this way. So there is necessarily, in fact, this was something that was stressed in the literature. We need to have a non-classical region, which is not the solution of the vacuum Einstein field equation outside of the horizon.
The problem is that there is a competition between the accumulation of these quantum effects and the presence of the time dilatation. So there is like a soft spot between getting as close as possible to the horizon, but not having too much of time dilatation. And there was this heuristic calculations pointing to a place that is 7/6 of the Schwarzschild radius to have the maximum of the effect. So I don't know if you are finding something. I don't know, because this calculation was just heuristic, but being heuristic was using minimal ingredients. So I don't know if you're finding something like this.
Follow-up is another one question. So the follow-up, so sticking with the simplification that we have an eternal event horizon and maybe also the Cauchy horizon. So could be that the bounds, so the transition bounds, just happen just before the formation of the Cauchy horizon, but still, since nobody knows exactly what the precise order of magnitude at which quantum gravity kicks in, so just before the formation of the Cauchy horizon, but and not obtain a displacement of the event horizon, because in a regular black hole, the event horizon is never placed at the same position of the Schwarzschild black hole. So, but not that tragic, that is compatible with the displacement of the event horizon and the correct observation.
Oh, you really don't like horizons? They are nice. They are.
Same. even to horizon 4, but then the bounce could happen maybe just before the formation of the Cauchy horizon.
Mm.
And in that way, you avoid all the
Oh, I
problems
see.
related to the Cauchy horizon. And second, I don't know if maybe the order of magnitude are not compatible, and then the event horizon displacement would be always not compatible to a bounce happening just before the formation of the Cauchy horizon. So it's a question. And second, it's about the stability of the Cauchy horizon. So let's say that the bounce happened after the formation of the Cauchy horizon,
Mhm.
and then Professor Liberati was pointing out that there are these problems of the stability of the Cauchy horizon. But there are a couple of papers by Bonanno, Savaresi, and
I don't think they are correct.
yeah, but wait, and they point, and also another one which we are working on, me with them, that they seems that could be the mass infraction instability could be cured in a more realistic setting, so that would not imply the pathological instability.
With respect, maybe if I understand what you were saying before, so that's right. That's what Stefano was saying before, that of course you have a singularity, but the singularity should be avoided by quantum gravity, even.
First of all, you don't need a Cauchy horizon for an instability. Cauchy horizon is good that they are unstable, otherwise you violate the strong cosmic censorship. So people doesn't like a stable horizon in general for good reason. But even if when you have a collapse, take Oppenheimer Schneider, you never form just an outer horizon. You always form also an inner horizon.
Mm-hmm.
The inner horizon in Schwarzschild, in a spherical symmetry crashes on the singularity, you forget about it. When you have a charge or you have a rotation, it stabilizes. The inner horizon, even if it's not a Cauchy horizon, so you still have a dynamical situation, but it's slowly evolving, and it can be rigorously stated how much slowly evolving it should, what are the slow evolving mathematical conditions. You still have an exponential instability. And this exponential instability is generic if the perturbation you are putting in are not exponentially small. And this is also solving the problem with the cosmological constant. With our cosmological constant, you cannot stabilize an inner horizon. You need really something that dumps very much the observation, the perturbation. This is a classical instability. And this classical instability, even in the case in which it's tamed and become a power law, it becomes a power law after being exponential for a long time, or at least long enough for being out of the where you need to do back reaction. So we don't know the end point of the evolution. See? But what I'm referring to is even worse. It was reasonably late understood, and again, to my surprise, that if you take the Uru state, the state that you want to have in order to have a regular horizon, outer horizon, and having docking evaporation, you have an instability in the inner horizon. The inner horizon, the semi-classical calculation tells you that there is an infinite accumulation of energy, which is ruled by the difference of the square of the surface gravity. So it's not even enough to have a degenerate inner horizon. I tried a model like that. If you don't have even a degenerate outer horizon. So this is there is a calculation by Barcelona and collaborator that is showing that this semi-classical instability is even more wild, more strong than the mass inflation one. So what you have is that when you form this inner horizon and try to stabilize it to get toward the stationarity, mass inflation tries to push it toward forming again a singularity. And this semi-classical one, at least at the start, seems to push it outward, toward the outer horizon, to crash the algorithm, which seems to be the source of the problem. And that's it. This is where we sit now. But apparently there is no way to make this inner horizon healthy. And there is another class of black hole which doesn't have inner horizon. It's the one she was talking about at some point, which are the one with the wormhole throat. If you have a space like wormhole throat, you have a minimum radius and then you bounce back in another space. That you can put the throat in such a way that you never have an inner horizon, you don't have a problem. But the problem with that is that if you want to create a geometry like this by collapse, you need to change the topology of special sections at some point. And that is something that quantum gravity may allow, but we are not able to describe with current calculations. Topology change is something we don't know how to do it. There was an idea. It was the idea, for example, in Euclidean quantum gravity, by which Hawking in 2004 was hoping to have solved the information loss problem, because you wanted to prove that basically in Euclidean geometry, you never have complex topology, the one associated to a standard black hole, but you had always global hyperbolic spacetime. If you have a global hyperbolic spacetime, the diagram, it will always be like that. And then everything that starts on Scray minus will arrive on Scray plus sooner or later.
Can I make a question, which is on a different topic? Okay. I wanted to ask you about the relationship between your narrative about black-white power diagrams with the friendly in the page first.
No.
Because that's rather well before string theory and all that sort of thing on page 3. Problems about entanglement entropy in the Hawking radiation, which has to reach a maximum and then decrease because you have less and less stuff to entangle with.
Yeah.
So how does that look from your point of view?
Well, from my point of view, the calculations rely on quantum field theory in a regime in which quantum field theory breaks down. And most importantly, the calculations completely disregard the presence of this very large volume inside the black hole. So when you reach the page time, you have the information paradox that appear. So the mismatch between the number of microstates for the black hole and in the outside. But again, if you allow for the presence of microstates allocated in this very large volume, then the problem is not there. And in particular, so the page curve is not simply the validity of the page course doesn't hold anymore. There is a paper on this by Carlo Rovelli. It's about 1 year or 2 ago that is specifically on this, and I don't remember all the details of it, but the core of the argument is exactly this: the fact that one has. So this is, I think, this is the big clash between the two communities, between the general relativity community and the string particle physics community. That is, the latter takes holography as a foundational thing, and the other community think about holography as a phenomenon that happens in certain regime, but it doesn't have to be taken as a foundational thing. And in particular for black holes, when you reach some paradoxes, it's exactly the point in which you are disregarding things like microstates that are not holographic. They don't stay just on the surface of your black hole, on the area, but they can be allocated inside.
Yeah, the question was for Professor Vidotto. So about the, I was thinking, so while the star is collapsing and there is the apparent horizon. So now going back to the fact that what we see are probably just apparent horizon attracted surface and not the horizon. So there should be an apparent horizon that forms outside the collapsing star, and the one that forms inside the collapsing star. And then there is the bounce, right? And the transition to the white hole. And it seems to me intuitively the bounce is completely symmetric. So in this simplification, during the later stage of the white hole explosion, anti-gravity is so strong that you would have like an anti-apparent horizon, right? That would be the time reversal of the.
That's the definition of the white hole.
Yeah, and then that at a certain point will, when anti-gravity gets weaker or because of the evaporation, it disappears, right? this anti-apparent horizon. And then bouncing matter could be observed in this moment. But I was wondering if some computation about the point of view of the external observer that has to wait this anti-apparent horizon to vanish, because the anti-apparent horizon could screen the bouncing matter arriving to us, right? And the commuting observer, that would be the collapsing star, remember, the floating star, has been done some calculation that can reconcile the time that the external observer has to wait and the time of the commuting observer, that would be the collapsing star, go through, if they are compatible, and then to observe this bouncing matter, the external observer, like, so if they are compatible, like, should the external observer wait an age that is equivalent to the one that would be the depth of the universe or whatever, or is it like could be useful, like with some constraint?
Yeah. Yeah, okay, very good. So what you are emphasizing is the fact that we have two different times, one that is for a infalling observer and one for an external observer. And because of the time dilatation, these two times for the same process are extremely different. So in particular for infalling matter, the process it's extremely short. It can be milliseconds or even less. So it's basically the time that takes to light to cross the black hole, to cross the star. So for a regular star, even just a solar mass star, this is of the order of the milliseconds. So if you do a very simple calculation, and you look at what this time corresponds in terms of time dilatation for an external observer, it takes billions of years. So this is what I was saying at the beginning, that so in this picture, instead of having a wormhole that takes you to a different place, you have a wormhole that takes you, well, you have a process that takes you to the future. So you enter inside, you go out, and for the external observer, you had billions of years that have passed. And this is actually very nice because in this heuristic picture, you have black holes that, as we observe them, that could be there out in the sky. And for us, they just look as standard astrophysical black holes, even though they have this fate on the very long term. So in this sense, everything is compatible.
We on Earth, to see the matter from the white advancing to our place, we should wait.
Well, and that's why you need the primordial black holes, because you can make a calculation and ask yourself since the lifetime always depends on the mass, you can ask what is the mass for which I can see, so assuming, say, that the black holes formed in the early universe, in the most standard scenario, like you have primordial black holes forming at the reheating, how much time does it take for them to be exploding today? So you have to assume a certain lifetime that could be m squared or m cube or some other function of m. It depends on the model. And so in order to do the phenomenology back then, we parameterized this lifetime, and we look at the possible emission for all possible lifetime from m to m cube. And so
it's billion of years computed from a primordial black hole.
So if they are
be observable in like,
if they are sufficiently small, they can be observable today. So we made a lot of phenomenology using this kind of reasoning, and then I also add in the jolly card that is okay. But then if they are from a pre-bounce phase, they can just be whatever, they can be they can have formed any time in the previous universe, so they can be exploding at any time. So this opens up the phenomenology.
For the Transplantian censorship criterion from conjecture. You know that in some cases then you switch from conjecture.
I've switched recently because some people don't like the proliferation of conjectures.
It's still something which I personally don't understand about this criterion, especially actually we don't understand which are the assumptions that are behind this criterion. And then maybe after I understand the assumption, I will be able to really get more convinced about that. Because the idea is basically that if you take some fluctuation today, some wave today, and you trace back them in the past, at some point they can become Transplantian. And you can compute basically this logarithmic time in terms of ripples. Okay, it looks like this. I mean, it's a very short time. But I think here the first assumption is that these fluctuations were really created in Transplantian region. But it could be that this fluctuation cannot really be traced back to Transplantian region because it was created in some subplanetary region first. Second,
right. So let me draw what you said. So we have the Planck length, and here we have H inverse, and this is tracing back the fluctuations. Now, what you're saying, maybe there is a new physics hypersurface where fluctuations are created. This is actually, I'm using words of Veneziano. So back after Jean Martin and myself talked about the Transplantian problem, then Veneziano and collaborators, and also Brian Greene and collaborators, they set up this idea. So the idea that instead of doing a usual Cauchy problem, where you set up fluctuations on all scales at some initial time, you are basically doing this. Now, from the point of view of unitarity, this is highly non-unitary because the Hilbert space is a product of Hilbert spaces of K smaller than K ultraviolet. So this is now your scale, K ultraviolet. And these are co-moving scales. So it would be KUV of T. So you see, even if you adopt this new physics hypersurface idea, you are violating unitarity.
My second point is that to explain why we don't have like something, reinflation was created in Transplantian region. Maybe we don't really need new physics, but for instance, if we assume that we have some very fast expansion in the universe, we have some expanding background, this would of course lead to some particle creation.
But that's the usual mechanism. That's the usual mechanism.
In this case, I would still say, okay, you are creating some fluctuation with some frequencies. Okay, there should be some spectrum. This spectrum will be picked.
No, because fluctuations are. So this is the way that the calculation is usually done. You basically say that there's an initial state psi of Ti, which again, it is a product Hilbert state of all k's of something that's the initial vacuum state, O of Ti. And then once OK of Ti, and once the wavelength becomes larger than the Hubble radius, this changes from being the Minkowski vacuum state to the squeeze state. So this is a usual theory of cosmological perturbations, Chibisov-Mukhanov.
Expect, like, for instance, that each fluctuation is created, for instance, if you assume some de-Sitter at the beginning and during inflation, I would expect, for instance, fluctuation to be weighted by some Boltzmann factor. For instance, if you have some Planck perturbation, you would have like exponential or minus n Planck over the temperature, or let's say the Hubble parameter during inflation.
Right. Now the point is that the the Gibbons-Hawking temperature has nothing to do with thermodynamics. Okay, so now if instead of taking this state, you take a thermal state during inflation, you will get the same kind of scale invariant spectra, because the only thing that's relevant for getting the scale invariance of a spectrum is that you have approximately constant H. Whatever you choose as your state, your initial state, you can take an initial thermal state in inflation, you will always get scale invariant. You just slightly change the amplitude.
I agree that H is approximately.
But that doesn't have anything to do with the TCC. The TCC is simply that there's a, so here you actually, if you adopt this new physics hypersurface criterion, then you're making the TCC stronger.
The assumption is also that, for instance, frequencies of the order of Planck scale or shorter equally probable.
They are not in the Hilbert space. They are not in the Hilbert space that will affect the field theory. You have to remove them.
So that you can equally, for instance, during inflation, you can produce waves with the frequency of the order of H or order of n Planck, and the probability for these two are of the same order. Or one of them must be more suppressed than the other, because you see there should be something.
Okay, so what you want to do is you want to take an initial state, psi of Ti. Let's call this vacuum. You want to take this as psi vacuum of Ti plus something else. Is that what you're saying?
If we look at the original computation of gravitational.
That's what we're doing. That's what you do.
Yeah, right. Based from Starobinsky.
Yeah, you do that for the gravitons.
So you have some explain the theta during inflation.
Yeah, that's it. That's exactly the.
Today you said so. But I would say that the spectrum is not like uniform across type of frequencies.
No, you get a scale invariant spectrum for gravitons. In the same way that you get a scale invariant spectrum for cosmological perturbations. The only thing that's different is the amplitude. The gravitons and the cosmological perturbations, if you look at the canonical variable, they obey the same equation of motion. So here I'm saying that that's a standard Mukhanov textbook. The fluctuations all start out as vacuum fluctuations of the canonical variable. And it turns out that there is this famous 1/epsilon enhancement of the scalar perturbations compared to the tensor perturbations. That's simply because the physical variable for cosmological perturbations is related to the canonical variable by this epsilon. So this was very conventional, what I said. So I ought to add something which is non-conventional. So you see that in all models except for inflation, the effect of epsilon is order 1. And so thus the statement is that in all models except for inflation, you get large amplitude of gravitational waves. It is only in inflation where you get a low amplitude of gravitational waves. So therefore, never ever was B-mode polarization the smoking gun of inflation, rather the other way around. If you detect gravitational waves with a fairly large amplitude, one more reason to throw out inflation. So I needed to say something provocative.
Thank you. We've filled the hour. It's maybe a nice closing point if there are no further urgent questions.
Thank you, everybody, for all the questions.
Then let's thank also our two speakers.